Welcome to this course on nanostructured materials, synthesis, properties, self assembly and applications. Today we are going through lecture number 12 of module 3, and this is the third lecture of the series of core shell nanostructures. And today we will do some applications of core shell nanostructures. So, there are many types of applications of core shell nanostructures depending on what is the core and what is the shell. For example, you can have a magnetic core and a non-magnetic shell, or a ferromagnetic core or an antiferromagnetic shell, or a diamagnetic core and a magnetic shell. This is with magnetism. Similarly, you can have a optical materials as core covered with a shell with a different optical property like a different band gap, and you can have core shell materials which can carry drugs to be used for drug delivery. So, core shell nanostructures have applications in a wide variety of technologies which are going to be useful in coming years to a large extent. So, the first example that we can discuss is a zinc sulphide core on with a shell of silica, and the core shell structure is not spherical, but it is in the form of a thick wire, or we can call them nano cables. So, inside this dark part is the core material we are calling, which is zinc sulphide, and on top of that you have silica, and this combination of zinc sulphide and silica core shell nanostructures can be used as sensors for finding out a particular biological molecule, and so these nano cables can be used as biological sensors. So, here a kind of a device is shown where you have the core shell nanostructure on top like this, and there are two electrodes, and you can measure the voltage across this. Now, when there is a molecule like the protein molecule, here it is a molecule BSA. Now, this BSA molecule, if it is on top of this nano cable where the surface is of silica. So, if this is having some charge, then the nano cable with silica on the shell normally has a negative charge. So, a protein which has a positive charge will sit on it easily, because this shell has got a negative charge, that is the property of silica surfaces, and since the protein has a positive charge, this protein here is bovine serum albumin, that is from the blood of, is a protein from the blood of the a bovine like cow, and this protein has a positive charge and hence will be stabilized on the surface of the nano cable. Now, when that happens, then the conductance changes. So, here you see before the protein was attached to the nano cable, the conductance is somewhere here and it remains more or less constant with time. However, when the protein is on top of the silica surface of this nano cable, then the conductance falls. So, this signal of the drop in conductance will give you a sense of the biological molecule. So, such nano cables can be used to sense biological molecules. Here a particular case where the charge of the biomolecule is of importance, because that is bringing about a change in the conductance. So, what one is measuring is the conductance, and this fall in conductance can be quantified, and accordingly you can tell how much of the protein is sitting on the surface. So, this is an example of a core shell structure as a biological sensor. Now, this is another example of zinc sulphide silica nanocable as a chemical sensor. So, you have this zinc sulphide core, on top you have this silica surface with silicon and oxygen bonds, and on top of this you have a functionalized molecule with an ammonium ion. So, here it is protonated amine, and at a different pH, when you raise the pH, this proton will be lost and it will become simple NH2 group, right. And there are you have got these kind of OH groups at some of the silanol groups, which are in the OH form, in the hydroxylated form. Now, if you increase further pH, so you increase the pH and you have this amine group instead of the protonated group. At further high pH, even these protons from the OH groups will be lost. So, in the first step these protons will be lost, in the second step at higher pH the OH protons will be lost, and that you can see in the conductance. So, when you are having this configuration, the conductance is somewhere here, some 0.13 microsiemens at around pH 4, and it is more or less constant. And when you increase to pH 7, then this proton has been lost and the conductance falls, and then it continues like that till again you change the pH to higher pH. Now, you are at pH 10, the conductance falls further, because even the OH groups have been the protons have gone away. So, you can plot as a function of pH a variation in the conductance depending on these studies. So, functionalized nano cables. So, you have functionalized this core shell structure of zinc sulphide and silica, and you have these kind of SiO minus groups at higher pH, and NH2 groups are having NH3 plus. So, this kind of variation in pH is controlling the conductance, and it is behaving like a gate. So, this is well known in devices, semiconducting devices, where one controls the current flow through a particular voltage, which is called the gate voltage. But here you are doing this by varying the pH of the system. You can make the system act like a gate. Here it is acting like a positive gate on decreasing pH and a negative gate on increasing pH. That means, when you increase pH, the conductance is decreasing, that means charge carriers are less, and when you decrease pH, there are more charge carriers, and so the conductance goes up. So, this is another example of a nano cable, a core shell nano cable, which is acting as a sensor, and here it is a chemical sensor, because it is identifying the variation in the concentration of protons. So, it is a chemical object, and in the previous example there was a biological molecule which was being sensed by the core shell nano cable, and then it was a biological sensor. Here it is acting as a chemical sensor. Now, this is another example of core shell structure, where now it is an alloy particle forms the core. So, this is a transmission electron micrograph of a core shell structure, and these are like spheres, and the dark sphere, small sphere at the center is basically the iron platinum alloy, and the lighter coating or the shell is made up of cobalt disulfide, and these are spherical core shell nanostructures. And if you take the edax from the center of the sphere, that is point 1, you will get an edax which will show you iron, platinum and cobalt, all three, and the copper comes from the grid. Whereas, if you take the edax analysis from the shell, then the point 2, if your electron beam is going through point 2, then you will only see those metals or those elements which are present in the shell. And here you see you can find sulfur, which because it is there, sulfur is there, and you will see cobalt because cobalt sulphide is there, but you will not see any iron or platinum because they are in the core. So, iron and platinum is missing here, whereas all the elements you can see here, because when you pass the beam through one, it goes through the shell into the core, and you will see all the elements which are present in the core as well as the shell. So, these are edax analysis normally done in a transmission electron micrograph, transmission electron microscope by choosing the electron beam to fall on specific positions in the core shell structures. And that is how you identify that your core is made of iron platinum and your shell has got cobalt disulfide. Now, why do you make such a material? For some application, and what is the application here in mind? That the cobalt sulphide, which is on the outside the shell, it has got a polar surface and is also porous, because the way you make the shell using Kirkendall effect, you generate porous structure for the cobalt disulfide shell. So, there are pores in this shell, and from this pores, when this core shell is in a solution, it can interact with biological molecules in the solution, and then what happens? Oxidation of the core material, because whatever is there in the outside, if you oxidize the iron platinum, then the platinum is released, and then so when the platinum is released, it can go out of the shell and interact with the biological specimens and typically attacks the DNA and will damage the HeLa cells, which is a particular cell line, and that can be seen in this plot, that the cell viability percentage, it goes down with time, and this can be seen using different concentrations. So, basically you are making platinum ions interact with the DNA by controlling the shell structure such that the platinum is released only when it comes when it gets oxidized, and then it will be released, and then it can act with the DNA and destroy the DNA of the HeLa cell. So, this is a kind of a targeted drug delivery, because the oxidation of the core nanoparticles at the targeted site occurs, and then only the platinum is released, and the platinum then destroys the cancerous cells which are present, and that is kind of an example of using a core shell structure at a specific site. So, you are having a targeted drug delivery, you are targeting a particular type of cell, and you are delivering the drug, in this case platinum ions, at the site where you want it to be. Now, this is another example of core shell nanostructures, where the core is made of cadmium selenide zinc sulphide quantum dots. So, this mixture of cadmium selenide zinc sulphide quantum dots, very small particles act as the core, and you have on top silica nanoparticles. Okay. Now, what happens when you put them in a solution along with green fluorescent protein? Now, the red marks or the red points are places where the quantum dot silica core shell nanostructures are there. So, here also you can see red spots. So, in a particular solution, these are pictures taken in a confocal fluorescence imaging microscope, where you are having this core shell particles of quantum dots and silica, and you can see along with green fluorescent protein, and the cells are basically neural cell. These are some cortical neural cells, and you can see that the red particles, which are the quantum dots with the shell, they are the red ones, and the green ones are the GFP or the green fluorescent protein. And the property of the green fluorescent protein is it will be seen only where there are live cells. So, these are all live cells, and these are the core shell particles, and this is from another part of the cell of the solution where a cell is present, and you can see that the quantum dot with the shell is internalized. That means, it goes inside the cell, and the cell is alive, because you can still see the green fluorescent protein on the edge, and that shows that without inducing cell death, the quantum dot silica core shell structure can be internalized. So, this is an example of using a core shell structure to image, and later on after imaging you can try to deliver the drug and see whether it goes into the cell. Now, this is another example of another type of cells. These are called NIH3T3 cells, and here also you can see that the GFP protein are showing up. That means, the cells are still alive. So, these are typical regions from these places. This is an zoomed image of these parts. So, this belongs to this part, and this belongs to this part, and so these quantum dots with silica are mediated. They mediate transfection of this cell line, and the cells are alive, because the green fluorescent protein can be seen, they are expressing it. And so, this is enough evidence that you can use these particles for imaging and also for drug delivery if required. So, the two examples, the last two examples that we showed shows the ability to bind, transport and release DNA into the cell, and which allows the GFP, the green fluorescent protein plasmid, to be transfected, and human neuroblastoma cell lines. So, NIH3T3 and human neuroblastoma cell lines were used, and thus the quantum dot silica core shell structure allows them to be of value for nanomedicine applications. That means, we can use these core shell structures and take drugs and visualize where the drug is going without killing the cells. So, these two examples show the viability of these core shell structures to be used up in drug delivery and in nanomedicine in general. Now, this is another example of a core shell structure, where we have used a alkane thiolate functionalized core shell structure, where the core is made of iron oxide Fe3O4, and it is coated with gold. So, you have this iron oxide inside, and outside you have a gold coating. The purple ring that you see is the gold coating, and on top it is functionalized. This red color is functionalization by this alkane thiolate. Now, the thiol part will be towards the gold surface. So, this can be seen better in this diagram. So, how do you make this? First is that you first make iron oxide nanoparticles with standard procedures. Once you get this spherical iron oxide nanoparticles, then you use auric chloride, that is the starting material for making gold particles or gold surfaces. So, on iron oxide nanoparticles you put this auric chloride and you get this iron oxide core shell structure with the shell of gold, and then on top of that here you use mercapto undecanoic acid, which we call 11 MUA, to form the functionalization on top of the gold. And so, the thiol part will be of this, or the mercapto part, which is the thiol part, will link to the gold surface, this purple surface, and the red part is the long chain. So, it can be shown this part, if you see, the 1, 2, 3 layers are basically the iron oxide and the gold on top, the purple, and on top is this chain of the mercapto undecanoic acid. This is the 11 carbon chain. At the end you will have the carboxylate group, and so these negative ions will be on the surface. And this is the TEM image of this iron oxide. You can see at the center the dark spot is iron oxide, and this is covered with the gold particles. So, on top of that then you add this 11 mercapto undecanoic acid to get this core shell structure, which is functionalized with this long chain acid. Now, what is the use of this kind of a core shell structure? So, you have modified a core shell structure with a particular functionalization, and what is the application? The application is this, that at certain pH, which is suppose less than pKa, you will have all the protons, they are not hydrolyzed. So, you have all the protons, they are not protonated, it is an acid with the OH group, and at a pH which is larger than the pKa value, you will get these anions because the protons have been lost. And so, this will be able to pick up certain molecules, which this will not be able to pick up, because this is negatively charged, it will not be stable with negative or anionic species. So, if you choose 4 type of these species, say non-ionic molecules, anion surfactants, and some acidic compounds whose pH is greater than pKa, and finally, some acidic compounds where the pH is less than pKa. If you have these 4 type of molecules, then this form of the functionalized molecule where the pH is less than pKa will bind to all the 4 different types of species. However, when at higher pH, when these will be having negative charges, then they will not like to bind negative or anionic species, and hence you see these are anionic surfactants, these green ones, they will not be adhering to this surface. Similarly, these acidic compounds whose pH is greater than pKa will be having O minus charges, and hence they will also not be amenable to be adsorbed or bound to the surface, because the surface itself has negative charges. So, this is like a filter where out of these molecules 4 of them only 2 will be bound to the surface, whereas the other 2 will be released. So, this is a good application of these core shell molecules, which have been functionalized by mercapto undecanoic acid, and it is pH sensitive with respect to certain molecules, and hence it only binds to certain molecules at low pH and certain molecules at high pH. So, that we can see here at pH low pH it is binding to almost all the systems of choice here. At high pH, when it is greater than pKa, then it is only binding to those systems which are neutral or positive, and this can be plotted in a curve that at low pH you see the amount adsorbed is high for certain molecules like SDS. At high pH, because SDS is negatively charged, at high pH when it is greater than pKa, then you will have carboxylate groups on the surface, and once you have carboxylate groups on the surface, it will no more adsorb the SDS, because SDS itself has a negative charge, and so there will be a drastic drop in the amount of material which is getting adsorbed on the surface. So, similar things have been done with other molecules where there is a drop at different pH. For SDS, the pH at which it drops is around 6. For nitrophenol, the drop is around pH 10. So, the drop can vary, but in all these cases it drops after a certain pH, and this is because of the surface charge of the functionalized group, which is generated when you change the pH to a value which is greater than the pKa of the acid group. This is another example towards medicine, where vancomycin, an antibiotic, is functionalized on a core shell structure. So, you have a core shell structure, basically the core, the inner core is silver, and outside you have titanium dioxide, and this antibiotic vancomycin is attached. So, we say functionalized to this core shell particle, and then we use two properties. Why this is important is two properties will act. Vancomycin is an antibiotic, and silver titania is a very good photocatalyst. So, the synergistic effect of the photocatalytic activity of the silver TiO2 core shell structure and the antibiotic activity of vancomycin. So, it will be a dual approach, and you will see the effect, it is called the synergistic effect, because two properties are acting in synergistically. So, how you make them is you first take silver nanoparticles, you make silver nanoparticles, then you make a silica layer on top of the silver nanoparticles using tetraethoxysilane, and on top of that you make a TiO2 shell using titanium isopropoxide. So, actually the silver is inside, in between there is a silica shell SiO2 shell, and on top of that there is a TiO2 shell, but together we are currently referring to this system as silver TiO2 core shell structure, and we are not referring to the silica which is in between. Now, to this silver TiO2 core shell structures, to attach vancomycin, it is first necessary to add dopamine and another molecule DSS, which is subbaric acid bis N hydroxysuccinamide ester. So, this molecule DSS and dopamine help vancomycin, which is an antibiotic, to bind on the TiO2 shell. So, these black fork like things are basically showing you where vancomycin, the antibiotic, is bound on the surface of the core shell nanostructure. So, once you get this vancomycin core shell nanostructure, then it can be used to act against some bacteria etcetera, and study the bactericidal activity for gram positive bacteria. So, one of these is SRB, and we will study under UV light, because we know that silver TiO2 core shell structure is a UV photocatalyst. So, what happens when you react this silver TiO2 core shell structure conjugated to vancomycin, the antibiotic, with a sulfate reducing bacteria. So, these molecules attach to the bacteria, and then in the presence of UV light it degrades this bacteria. So, the rate of degradation is much faster if you use a combination of silver TiO2 and vancomycin instead of just silver TiO2 or just vancomycin. So, because two properties are acting simultaneously, one is the UV photocatalysis of silver TiO2 and the antibiotic property of vancomycin. Now, we can also make hollow shells. We were discussing core shells, that means there is a particle core material on top of which there is a shell, and that is the core shell structure. Now, we can also make use of hollow shells, that means there is a shell with nothing inside. So, how do you make such hollow shells? For example, you take this core shell structure of cobalt oxide and silica on the outside, you put it in sulfuric acid, and then the core is eaten away, and what is remaining is the hollow silica shell. And how do you know that the hollow silica shell is formed? Is basically you will have from infrared spectroscopy, you will see the vibrational frequencies corresponding to OH groups, then SiOH group and OSIO stretching frequencies, and you will not see any frequency due to cobalt oxide, which you can see in the original core shell nanostructure. From electron microscopy also you can characterize such core shell structure. So, you can see these thick or dark particles of cobalt oxide surrounded by a thin shell, and you can do a EDAX, that is energy dispersive X-ray analysis, and you can see cobalt, silicon, oxygen from here, copper from of course, the TEM grid, and in the hollow shells you can see that only the shell is present. This internal part which was dark in here is no more there, and these are the hollow shells you got after you treated the core shell with sulfuric acid. And then this, if you look under the TEM, you get this image, and if you do energy dispersive X-ray analysis, you will see only silicon, oxygen, and of course, copper from the grid and carbon due to impurities. You do not see any cobalt peak, which you can see here, which shows these are hollow shells. Now, how you can use these hollow shells is, for example, you can trap some organic molecules which act as pollutants, and here you show that this is the shell, and these are like your organic molecules which cause pollution in the water, and if you put the shells in water, after some time these shells get trapped inside. And how do you know that the shells are trapped? What you can do is you can measure the UV visible spectroscopy corresponding to the organic compound, and the intensity, suppose the absorption of that organic compound is a peak around 500 nanometers. Then if you monitor the peak, as the organic compound is getting trapped, the intensity will become lower and lower. So, here you can see that the control experiment is here, which has the and after 1 hour, 2 hour etcetera, the intensity is decreasing. So, for 2 hours you see the green one, and then after say 48 hours you can see this black one for 48 and 72 hours. Now, so the intensity of the organic compound, which was methyl orange in this case, decreases to some extent and then tries to become constant, and the decrease is around 20% here, but you can get much higher decrease if you can design for other types of larger hollow shells. But what this shows is hollow shells can trap the organic pollutants. Now, this is an example of measuring or knowing that it is a hollow shell. Again, by TEM you can see that, but you can also use gas adsorption, which you can easily do in a surface area type of measurement, the BET method, and you can show that nitrogen adsorption increases. So, initially the particle surface area that you obtain from nitrogen adsorption experiments is around 103.1 meter square per gram. After some time it shows a surface of 191.8 meter square per gram, and this increase in surface area is basically because of increase of nitrogen gas inside, and that shows that it is a hollow shell to start with, and hence can take up nitrogen gas. And so, the finally the surface area that you calculate will be much larger in the case when the nitrogen is adsorbed by this hollow shell, and that is exactly what happens. From 103 the surface area goes to 191.8, and this is another proof that you are dealing with hollow shells. Now, this is an example of making movable silver cores inside hollow spheres or hollow shells. So, you have to start with a polymeric hollow nanosphere, and you want to make silver particle inside, but not the entire region should be covered, but only a small region should be covered with silver. So, that the silver particle can move around this internal surface like a ball. So, what you do? You first make this hollow sphere of a polymer with chitosan, CSS chitosan, and this is polypyrrole. To get this hollow sphere, you start from chitosan, which is shown here, and you use silver nitrate and pyrrole and F is iron chloride, and you get silver chloride particles. Okay. And then you polymerize and you get the polymer with the chitosan which is there, are forming a shell around silver chloride. So, first silver chloride forms, and then this silver chloride is inside, and this polypyrrole chitosan core shell structure is formed. Then you add ammonia and ammonium hydroxide solution that eats away the silver chloride. So, it dissolves the silver chloride which is inside. We call it etching. Etching means removal of something. So, you are removing silver chloride by using ammonium hydroxide, and you are left with only the shell. So, you get this hollow shells or hollow nanospheres of polypyrrole and chitosan. Now, you take these hollow spheres. So, the PPYCS hollow sphere you take, add silver nitrate at a certain pH, and you have got silver ions inside and outside. You remove the silver ions outside by dialysis at a low pH, and you are left with a shell of this polypyrrole chitosan with silver ions inside. And if you now bring a UV lamp near this particle, the silver ions will get reduced under UV radiation, and they will become silver particles. and so you will get this silver particle inside the shell. And so, this is a small particle. So, it can move around inside the shell, and this is the TEM picture to show exactly how this looks. So, you can see that dark spot here, that is the silver particle inside the polypyrrole chitosan shell, and this has interesting applications of when the silver particle can change positions within the hollow shell. This is another example of how a hollow shell can be used to make a core shell structure. So, this is an application of making a core shell structure starting from a hollow shell. So, you start with a hollow shell of silica, there is nothing inside here, this is silica shell, add auric chloride, that is the source of gold ions, and then once you add auric chloride, then you add sodium borohydride. Sodium borohydride is a reducing agent, and it will reduce the gold ions which are here inside to form gold particle. So, you will get gold which is encapsulated in silica. So, this is the picture, you can see the hollow silica, and this is gold inside silica. So, these dark spots here is gold silica made from hollow silica by reduction with sodium borohydride. So, this is an example, very good example of gold silica core shell structure being synthesized from hollow shells of silica. Now, you can also make oil filled silica nanocapsules for taking drugs or medicine which are lipophilic, which means they like oil phase. Lipophilic means, philic means something which likes, lipo means oil. So, something which likes oil, which is soluble in oil. So, that kind of drug, if you want, then the oil phase should be inside. So, oil filled silica nanocapsule you have to make. Now, how do you make this oil filled silica nanocapsule? Is you start with this is a microemulsion process. So, in a microemulsion you need a surfactant, an oil phase, and an aqueous medium. So, the surfactant here is a neutral or non-ionic surfactant whose common name is bridge 97, and this is the structure of the surfactant. So, there are a lot of ether linkages as you see in this bridge 97 surfactant, and typically most of the non-ionic surfactants have this kind of a polyether linkages. So, if you take one, which is this surfactant, plus you have this molecule which is the non-aqueous medium or the oil which will be inside, that non-aqueous hexadecane you add along with this oil phase is the hexadecane phase, and this number 2 is actually octadecyl methoxysilane. So, this octadecyl methoxysilane with the hexadecane oil, that you will mix along with the surfactant and water, and when you mix all these 4, the surfactant, the oil, and this octadecyl trimethoxysilane molecule and heat it, then you get this kind of a oil in water microemulsion. So, here the oil which is hexadecane oil, which is will be inside, and these long chains, are the hydrophobic part of this surfactant molecule, which is bridge 97, and you have this on in this inside you will have the hexadecane oil incorporated. Now, then you add your this TOS material, this silane, and then you get this core shell material with silica on the surface. So, silica will bond like this, and you will have a shell of a polysiloxane or polysilicate if you want, and this is filled with oil, and the hydrophobic chains are all pointing inside towards the oil. And the hydrophilic part, these circles show the hydrophilic part, that is the hydrophilic part or the polar part of the surfactant, which are the ether parts, the oxygen parts, they are on the surface of this micelle, as also you will have the octadecyl trimethoxysilane will be there, and tetramethoxysilane you add at step 3 to form the shell. So, the shell is actually formed when you add this tetramethoxysilane, and this has formed, you can know by doing a transmission electron microscopy, where again you see the oil phase, which is here shown in dark, can be seen only when you use a stain. A stain is added to enhance the contrast in the electron microscope. So, that stain is basically an osmium complex, is a molecule of with containing osmium, which is doped along with the oil. So, wherever that oil goes, this osmium molecule will go, and since osmium is a heavy metal, it has many electrons. So, it diffracts or scatters the incoming electrons much more efficiently, and so you will see that portion to be very dark, because the contrast will be high whenever you have more scattering from that region. So, this portion as you see is darker because of the osmium stain that you have used and doped in this oil. So, this is an example of an oil filled silica nano capsule which you have made. Now, you can use this for uptake of a drug which is soluble in oil medium, because you have an oil medium inside. If you take a drug which is soluble in oil and you are able to solubilize in this micro emulsion, then the drug will be stable only in the inner part, because that is the hydrophobic or the lipophilic part, and the drug will not go to the shell, because the shell is hydrophilic, and this can be studied by looking at say a drug like quinoline. So, you add quinoline. Quinoline is organic in nature. So, it is kind of a non aqueous. So, it is more like an oil, and this drug will like to go in a place where it is more lipophilic or more hydrophobic. And if you look at the change in quinoline in the solution outside the microemulsion. So, when you add quinoline, some quinoline will be outside and some quinoline will go inside, which will go into the lipophilic region, and with time there will be more quinoline inside than outside, because the drug is being taken inside that portion which is of similar type as the drug, and since the drug likes an oil type of environment, a hydrophobic type of environment, hence the oil will go, the drug will go and sit where the oil is present, and the oil is present in this dark part. So, if you give sufficient time, then the oil will slowly move into the darker region which is the core of this core shell structure. And so, with time if you calculate the quinoline which is outside. So, the drug which is outside can be easily found out by doing an experiment, and that experiment is basically looking at the UV visible spectroscopy of quinoline. So, quinoline has a particular absorption, and if you do the UV absorption of quinoline at 299.5 nanometers, if you look at that, then with time as you see it will drop. So, that says that the quinoline is less outside after some time and more inside. So, uptake studies of quinoline basically shows that initially there was lot of quinoline in the solution because it was not inside the core, but after some time that concentration of quinoline decreased with time because the quinoline was going inside and it cannot be found in the solution outside. So, in the measurement you only measure when the quinoline is outside the core. When it is inside the core, then you do not get this absorption peak, and hence with time you can study the fall of the quinoline absorption. And with nano this now we can call it as a nano capsule, because all of you know what is a capsule. There is a medicine inside and there is a cover, and inside the body the cover will dissolve and the medicine will come out. Similarly, this is a nano capsule because you have a cover and the drug is inside, but this is not a capsule which we can hold with our hand, because this is very small, and this is called a nano capsule, because now you have very tiny capsules of the diameter of 100 nanometers, where the core is probably only 15 to 20 nanometers. So, the drug gets encapsulated within that 50 to 20 nanometers. You can study as a function of time this uptake of quinoline, which is given by the decrease in the intensity of the UV absorption at 299.5 nanometers for quinoline. You can also vary the concentration of the nanocapsule solution and free quinoline. If you plot that, you see the free quinoline is decreasing as you are increasing the nanocapsule solution oil content. That means, if you this oil content is very large, then you can take more drug inside. So, that is what you are doing. If you increase the amount of the oil which is in the core of this core shell structure, then the free quinoline is much less in a capsule which has got more oil, because obviously more the oil, more quinoline can be trapped inside the core shell structure. So, this is what you can do with the study of core shell structures of molecules which are lipophilic in oil filled nano capsule, and is a very important application of drug carrying capsules to targeted sites within the body. And if you can target such capsules, you will need less quantity of drug to attack the same amount of bacteria or other diseased cells. So, with that we come to the end of this 3 lecture part of core shell structures, and this was the lecture 12 of module 3, and we have 2 more lectures in this module to complete 14 lectures of module 3, and those 2 lectures will be given in the next 2 lecture classes, which will be on nano composites. And basically we finish our study on core shell nanostructures, which has tremendous applications, especially in drug delivery, in nanomedicine, in protection of particles with mechanically stable shells. And now, we will move on to the subject of nanocomposites in our next two lectures. Thank you very much.